So let's move on to more exciting things. Pictures from my summer vacation. Let's see, where did I want to go? I wanted to go here. Yep. So I went ahead and prior to class composed some notes, which of course will appear in today's class notes. Reviewing a little bit some of the declarations that are important to us that we find primarily in Bison. The first is we have this token declaration, which we need one of for each terminal token. And one of the primary things it's going to do, again as review, is going to convert this into an element of an enumeration, so there will be some numeric value attached to this. And that enumeration is required because we need a way for our scanner to communicate with our parser, and we will do that through these terminal tokens, right? A terminal symbol. A terminal will be matched by the scanner, then it'll return this representation of it, and then we're able to use it on the parser side. So this declaration creates that enumeration, allows that. We also have, not with every terminal token, but with many, well, I don't even want to say many, with some of them, there is a type associated with the semantic value attached to the token. So the token could be a t-constant integer, and then if an integer is found by the scanner, then the t-constant integer token is returned, but the actual value, the integer that was found, would be the semantic value, and we need some way of representing that, associating this token with that type, and that's done here. We have I guess I'll add, maybe I'll do it right here, a union declaration. And so this is where we are going to specify our types that can go back and forth, the semantic values from the scanner to the parser. And we'd have stuff like this. A note about the unions is unions do not handle class types well. So for example, a string, as you would expect, if you were to crack open the private data of the string class, it would have an integer representing the length of the string, for example. But something that also exists inside of that string class, or I should say that string, any string object you create, is going to be a pointer to some dynamically allocated memory storing the actual contents of that string. All right? And as we saw with when we were talking about unions last time, the memory allocated doesn't change, it's just our interpretation of that memory. And storing if I have a complex type in there and one piece of data, that complex type, is a pointer to somewhere else, it just isn't going to work well because that union gets used and reused and you end up leaking any dynamic memory that has been allocated in the object. So that's just a long way around of saying that if you have some sort of complex type, and when I say complex type, I mean any type that is of class type, then you need to work with pointers, because this is just going to be 4 bytes or 8 bytes or whatever the architecture requires for the size of an address. And that there's no problems with managing an address in a union. Yes? Because it's just a number like an integer. Yes?
And what if, like, in the flex side, we go and we allocate a new object of that and assign it to the pointer?
Mm-hmm.
Well, what if in the Bison side, we use it and then right after use, we destroy it, we delete it? so we don't have a memory leak, and because we got that token, we know that there's a valid object being allocated. So we just don't need that to use it, like a one-use type thing.
All right, right. So for the sake of the recording, what was said is, what if on the scanner side, on the flex side, there a regular expression matches like a string constant, and so you need to return some sort of token indicating that you found a string constant, and then on the scanner side, to YYL val, the union string, you're going to assign basically a dynamically allocated string, right? New string, and then whatever the contents is of the regular expression found. And then, so let me stop right there and say, yes, that's precisely what you do. So that isn't just a theoretical what if, that's a practical, that's how you do it, right? Since the only thing we can store in this union is a pointer, we have to allocate something dynamically and assign it to that pointer on the scanner when we find it. And I made mention of this before, and I'll be making mention of it again. It doesn't have bearing on project 1, but in later projects it has great bearing. In general, developers are not concerned with memory leaks in things like compilers, because a compiler in a smallish program is only going to be in existence for at most a few seconds, right? So if you leak some memory, it doesn't matter. In a few seconds the program goes away and that memory is reclaimed by the operating system. Memory leaks, of course, are more a concern in a long-running game or in some sort of utility application that you have running for a long time, where memory leaks can eventually hobble the operating system. That said, you all have, to the extent that your experience is based on courses in this program, you all have not had a tremendous amount of experience dealing with dynamic memory in really large, complex projects, which is precisely what this is. So not for every project, but there are 2 or 3 of them where I'm going to require one of your criteria for delivering a successful project being that you are cleaning up all your memory leaks. So that gets to the second part of what you're saying, which is on the parser side. After you grab and make use of that dynamically allocated string, once you don't need it anymore, that you would indeed release it to maintain memory integrity. Okay. So we have that to look forward to. Let me see. Let me put a little text here. So this is declare the types used by semantic values found by the scanner. And so what we would have here is the name of that union member, which in this case would be union int, union double, union string. Of course, these names can be any valid identifier. What we'll find is that in GPL, there is some code that you are using that you're not writing yourself, and the standard that code settled on was the word union and underscore and then the type that follows. You're welcome to change that. That just means you have to go into some code that you were given and change it there as well. If you want the path of least resistance, these are kind of going to be the names of your union members. As we get further down the road, this union is going to grow fairly large actually, and then you'll be, for the more complex types that are of your invention, you'll be at complete liberty to give whatever names you want. But early on for these set types, I would counsel that you just go with the names that I proposed here. The token is required of all terminal symbols, otherwise you're not going to generate an enumeration code, which means that the C code generated on the scanner side isn't going to compile, because it basically the token for which you did not have a declaration would be undefined. There's a bit added here which I haven't talked about, and you can go ahead and have a literal string here following that token declaration. And if you do that, there are a number of contexts where it is taken advantage of. I'd say one of the main ones that's useful to us is that when there are errors generated, the text of that error will be whatever you have here. And so that can be useful instead of looking at having a token that is like t greater than or equal to. You can do something like this, right? And then that'd be much easier on the eyes when you're looking at error messages. So that is the motivation for having this here. Okay, the union we talked about. Next, we have non-terminal symbols. So again, the non-terminal symbols are things that you can find them on both the right and left-hand side of productions. Whereas to differentiate that from terminal tokens, the only place terminal tokens are on the right-hand side of the production rules. So some combination of terminal tokens and non-terminal tokens will reduce down to some non-terminal token. There are cases where non-terminal tokens need a type because there's a semantic value going to that because it's later going to appear on the right-hand side of some other rule, and you'll need that semantic value. So for those non-terminal tokens, you need to have a type declaration. I do want to emphasize that you do not have a type declaration for every non-terminal token. The vast majority of them, you don't need any declaration at all. The purpose of this is to tie some sort of type here to that non-terminal token. And then we have the declarations here that indicate associativity. So if you have %left, then the tokens that I list here are going to be left associative, and the generic example given here is that if I have A operator, B operator, C, and if that's to abstract A plus B plus C, if it's left associative, then the A plus B is going to be handled prior to the result of that being handled being married with C. That's differentiated with right associativity, where you're going from right to left, and we saw an example of that in the C and C++ language, is assignment is right associative, goes from right to left. I will note that in GPL, the assignment operator is considered a statement, not an operator. So you won't, for assignment, you won't have be specifying any sort of precedence for it. It's handled differently in GPL. And then to tie these two together, they're going to be in. You're going to have presumably several of these %left, %right directives. Most of them are %left. Most operators are left associative, and their order indicates how high the precedence is. And the higher up in the file, meaning the earlier the line number that it appears, the lower the precedence. And the precedence increases as you go down. So to put more concrete words to that, %left plus minus is going to appear before %left multiplication and division. Yes?
So it's like in CSS, if anyone of us is familiar, rules that more specific rules of CSS, more precedence, they go down.
Yeah, I guess looking at the way CSS handles it is certainly one way of looking at it. There's a final one, which is there is a precedence. Again, this particular declaration would appear right in there with the lefts and the rights as one, which is non-associative. And some of the operators are non-associative. And first, what that means is if I saw that operator in this context with A operator, B operator, C, that would be an error because there's no association that occurs left to right or right to left. The real obvious non-associative operator is just the negation operator. So for instance, -3, -4, -5, there's no valid mathematical construct this way. That negation doesn't associate, because what happens is we end up using that operator in a different context, which is subtraction. Right? So note that definitely this minus sign is bound to this 3, but there's no association with other terms. All right, so that covers it for kind of the meat and potatoes of what we need in Bison. There's something I didn't talk about, which I want to touch on a little bit by going back to some stuff that I threw up last time. So recall, I guess that we can start with the scanner side. So the scanner was quite simple. It just simply identified integers and then addition and multiplication. It basically ignored everything else. And then on the Bison side, we indicated that we had 2 tokens, addition and multiplication, and the integer. The integer is going to have that semantic value associated with it, so we have the union member listed here. And also here's the example of the non-terminal having the type associated with it. And we scroll down here and we have the rules shown. And this illustrates why your non-terminals need to have a type, at least this non-terminal does, because what's going to happen is the 5, if we're going to do addition, we hit this rule here, it's going to grab the 5 plus 4 and it's going to calculate 9. So these positional arguments are referring to the first, second, and third. That answer, 9, we have to do something with it, and the whole idea is that non-terminal, which is on the left-hand side of this production, is represented by $, and we are then storing that semantic value of 9 inside of EXPN. So this is EXPN 9, and then of course we hit this rule once again, and this time this EXPN has the semantic value of 9. And then I haven't gone over this, obviously gets converted to EXPN down here. The integer gets converted to EXPN, then it ends up in this rule. So there's our justification for needing to have semantic values associated with some of our non-terminals. What I wanted to show, so I can say Bison and I suppose I could do some, I'm not interested in the compiling. All right. What happens if we leave off the precedence? You get shift reduced. So let me take away where we indicate that addition occurs before multiplication. Now when I run it through Bison, it shows me that I have shift reduced conflicts, which simply means that as it was processing those rules, it found that there are ambiguities, and there are certain points in time where it was equally valid to either shift another item onto the stack or to reduce what was on the stack, right? And in later projects, you're going to want to be able to identify where is it actually having problems, because this isn't very informative at all. And there is another flag you can add, which I assume means verbose. And if I do that, it creates this file with a .output extension. And if I look at that file, then it shows me, so let me back up a little bit. what this file contains is kind of a human-readable version of what the parser creates, and it just creates this big state machine. And what this is indicating is that states 7 and 8 have the conflicts, so you would go ahead and jump to one of these states. And really, you can kind of puzzle over this stuff and see what it's telling you, but kind of the easy way of tackling this is just look at this right here, because that shows you which production it has problems with. Then you can stop right there, go into your bison file, and start staring at that in your bison file, that particular production, and see if you can, and then you'll see, oh, there's addition and multiplication. Well, maybe I have problems with my precedence with those, right? And that's kind of how you can go about debugging that. So I wanted to throw that out. If I, just to show you, if I go ahead and fix that grammar and add the precedence back in, and note I still have the -v options, so I should still have that output file created. And if I go to the top, you'll note that there's no complaints up there at the top of the file. Okay, but otherwise you're welcome to go ahead and look at the state machine. All right, so there's that. I think that then takes us to the first project. So let's see, I'll go here, and there is a tarball you can download, so let's download that tarball. Oh. Okay, let me do that again. All right. So this is my 515 work. I'll create a directory for that. Let me go back over here to where I'm actually in a vagrant machine. And what I'll do is I'll cd into my 515 work, and I'll extract maybe show it to you in a form you may not have seen before.
So it can take a tar file as standard input.
Yes, by default, tar wants to work with standard input. Actually, and if you go way back, tar stands for tape archive. It would normally interact directly with the tape device, right? And it would dump it straight to the tape device. Nowadays, no one knows what tape is, so it just dumps to the screen.
What if you figure out the internal format structures of a tar file, and then you invoke the tar command and you just start typing on the keyboard? Would that work to extract the so-called files?
To work on a document inside of a tarball?
I mean, so the tar command, it accepts from the standard input, right? It accepts a file. What if you just type something in? Oh
yeah, sure. You could manually create a tarball. Yes, absolutely. That'll be your project for tonight. So yeah, so you can see it's obviously quite readable. I mean, relatively speaking, right? It's clearly not some sort of binary. All right. So what did it create? Let's look at what it created. So let me throw another one. All right, so I did that, which is the tar command with T, which is to see the titles inside the archive. And it creates a bin directory, a source directory, and inside of source it creates P1 and a bunch of stuff inside there. We're actually going to look at all this, so I'm not going to go into detail here, but if I go to the bottom of this, I also added this at the 11th hour. It creates P2, P3, P4, P5. One of the things that you are provided is a makefile, and the makefile operating correctly depends on the parent directory, or the directory that you are inside of for that particular project being P followed by the digit being the project number. Okay, there are pound defines that it sets. An example of a pound define it would set is these early projects, we don't need a graphical interface at all. And so it sets a pound define that basically will omit all graphics related code. Okay. So let's take a look inside of source first, and then there are the projects that 2 through 5 are empty. P1's the only one it's filling up. And what I'm going to do is I'm going to bring up readme_p1.html. That one, you'll notice here, it's both in the tarball, and I actually have it separate as a link here just for convenience. They should be identical. And here's that. A bit of errata at the top, summary. So what you're going to do in this first project is we are going to basically get your scanner and your parser in place so that you can compile this thing successfully. Okay? It includes the file we're reading. I did this in Markdown. It's not included for any reason other than that's where it was sitting. GPL.cpp, we can look at that. It has a fair number of comments in here. So to the extent that you like digging through this code, you're welcome to. This is all, basically this is kind of the bootstrap code that gets the whole GPL environment initialized. Also, if you recall, when you would run your GPL program, you know how on the console it would dump all the variables that you declared and that kind of thing. All that's handled in here. Okay? And things like if there's an error in parsing, you then do not want to go on and start interpreting the program because there's a bug in it, right? So all that decision making is done in here. What else do we have? We have GPL assert, CPP, and H. This is used if you're using like GDB as a debugger. And what happens is normally you're going to, most of your code, a lot of your code is going to be sitting in the parser eventually. And what happens is if you use the assert statement, then it's going to give you a location inside of the C code that it compiles, not inside of the .y, the parser file, which is where you're interested in finding the problem. So this is just a bit of wrapper code to make the assert statement in the C language more useful to you. If you don't care to use it, that's fine. You don't have to use it at all. We have a number of text files here. I will talk about those in a moment as far as how they relate to doing the directions here. And we have a make file. Parser.h I will talk about in a moment. And then I'll talk about tests and more text files. All right. So let's go to this description after the manifest. This is just a quick review of what we're already aware of is this general format for the bison and flex files. And then there's the project description, and it is separated into things that you should do. So let me do the first couple here. The first thing I have you do is copy scanner skeleton into gpl.l. and the parser skeleton into gpl.y. The reason I do that is why am I having you do that busy work? Why didn't I just call these GPL.L and GPL.Y? The reason is that in the past, people would do some work and then for whatever reason decided they needed to extract the tarball a second time, and it would overwrite their GPL and .L and Y. So this, now I no longer in the tarball have a file by those names, so I won't overwrite your work. All right. So we see these options that we became accustomed to before. We're going to get the scanner jam error if we have some sort of unhandled character. This is because we don't need to process multiple input files. All right. Here's where you normally have the .include for the tab.h. Again, I'm in the .l file, and this is the file that's generated by Bison. Right? It generates both the .c and the .h. This contains those enumeration constants. That has been moved into a different header file, parserh.h. So let me actually look at parserh.h. And here's that include. So there's kind of a problem with, as this project goes on, you're going to have more and more header files that need to be included. And rather than you trying to get them in the right place inside of the Bison file and getting them in the right place inside of the scanner file, the flex file, because you need them in both places, the idea is you just put them all right here and then make sure that they all occur before gpl.tab.h. Because the stuff in gpl.tab.h actually is going to require some of the information that you end up creating in your own header files. So that's just a long way of saying, moving forward, whenever you have a header file that you need to include, go to parserh.h and include it there. Don't put them directly in the .l or .y files. Okay? It'll save you a couple hours of debugging. That's what that comes down to. There's a class used for error handling, and the way that, and we'll get into how this stuff is, how you assess your progress and how things are graded in a moment, but the short thing is, if you're accustomed to that turn-in tool, which you probably would have gotten in 111, I don't know if it depends who the 311 instructor is, but that's that tool where you submit your code and it'll compile it, and if you have something wrong, it'll show you a set of differences. Same idea here, although we'll be running those tools manually. We're not using the turn-in web interface. And the key to being able to assess 35 projects that are fairly complex is to not allow you to come up with your own text for the errors. Okay, it would take, well, it'd take a long time to manually grade your stuff and have to go through it with a fine-tooth comb. It's far easier if the error messages are standardized. So that's what this error class is doing, is it's standardizing error messages. Let me actually pause for a moment and look at that. There is error.cpp and error.h. Let me look at error.h. Actually, let me look at, yeah, I can look at that. So there's some nice messages here on how to write error messages. Here's an example. Let me see if I can pull that out of comments so it's easier to see. So in the error class, you're going to call this error function. This is just an enumeration right here, which you can't see when I highlight. But that's just an enumeration, and then there's information provided that's pushed into the error message. So the way the process will work, and it isn't so much, we're about to do project one, and this really isn't that important for project one. It becomes more important later on when we're writing a bunch of C++ code. What you'll do is you will run your project, you'll compare it to expected output, and you'll find the expected output isn't the same. So you'll look at what the expected error message is. And the expected error message is undeclared identifier. Let's see if that's going to work. And so what you do is you go into error.cpp and you look for undeclared, and of course it isn't there. The word undeclared isn't there at all. You look for the text of the message that was expected. Let's say it was this one. The animations block your error message began, the animation blocks parameter. And you go, aha, this is the error message that I was supposed to push out, but I didn't. Let me see. Oh, I need to generate this kind of error. And so then you'd go back to your code and you'd say error, : error, and then in parentheses, this would be the enumeration that you would push into that call to the error function. So that's how these end up being useful. You end up searching them for errors that you need to report. And you'll be told if you didn't report the error. All right. GPL. Yes?
Why isn't this, like, why aren't error handlers done, like, as more standard things? So far,
Why aren't they done as more standard things?
yeah, this seems so much easier than having to write your own error messages, just a centralized thing.
Well, I think that is probably the case in large real-world applications development, right? They've created their own standard libraries, project standard libraries for all sorts of things, which would include error reporting and logging and things of that sort. So this is just an example of that. This is
Never mind then. I'm just inexperienced.
no, that's fine. All right.
It's a good idea for thinking.
All right, so this is, where am I? So this is the flex file. That's what this is. I talked about this last time. All these error messages will say your GPL code is all screwed up on line 53. And that is because this line count variable is being used. And so what you have to do is you need to increment this line count whenever you see a new line. And then finally, there's some other code here that that'll just be invoked internally, and you don't have to worry about that. You got to put all of your patterns here. It's going to be more than 3 lines, I can guarantee you that. It's going to be shoved in that space, though. And then a comment here. This is probably hard to read. It's probably easier to read if you're following along on your own computer. This message says this should be the last pattern. We talked about this before. If all else fails and nothing grabs, no regular expression you have grabs the character, then the last resort is to grab any single character and generate an error. And then note that it returns the TR token back to the parser. Let's look at the GPL.Y skeleton. So everything up to the 2% signs is that preamble stuff that's directives and code. And note that I have % open curly, % close curly for literal code that I have in here. Have some prototypes. Some header files are being thrown in there, including the big one, parser.h. All of your includes go in parser.h, remember. Here's that union. You're going to have to add union double to this. And then you're going to throw all your tokens here. Yes?
I have a question about the it seems that that union defines the data type for the YYL value.
Yes, this is describing the union that will be the variable that holds the semantic value that transfers information from the scanner to the parser.
How does it know to associate that union declaration with the YYL value? And what happens if you have more than one variable that you
It
would want-
that's by definition, this declaration is associated with YYL val
and where is that defined?
in the documentation for bison.
Oh, so it's built in.
Yeah.
Can you have more than one YY value?
Well, you can certainly crank your own. Right. You can declare whatever you want, and then just have it have an extern declaration on the other side and be able to access it from both files. All right. So now that takes us to tokens for bison and tokens for flex. Let me look at tokens for bison first. Okay, this file's 113 lines. It says copy the file. So a lot of this is done for you. Not all of it, but a lot of it. These are all the tokens that GPL needs to handle. Int, double string, those are easy. We have the shapes, triangle, pixel, map, circle, rectangle. Note that some of these have the angle braces. That means that it has a semantic value that needs to be passed from the scanner over to the parser. In this case, they tell you what it is. It's the line number, so this is going, what are you going to plug in right there?
Line number variable.
You're not going to plug in line number. That's the name of the variable we need to type. Union int. Which member of the union is relevant to the semantic value for this token? A lot of this copies. You don't have to worry about it. Here are 4 that you're going to have to do the types for these. All that gets slapped into the bison side. On the flex side, this is a list of regular expressions. So what does this regular expression match? Right, it's so obvious it's confusing.
Kind of question.
If you have an I followed by an N followed by a T in your input stream, this regular expression matches it, right? This matches the literal string int. This matches double string. A lot of these are obvious. So what do you have to do here? Send the token for int. What is this? Okay, not this, because this is the token for 346, right? A literal integer. It's this one right here. So if your scanner matches t underscore int, it needs to return t. If it matches this, it has to return t underscore int. You have to do the same for all these. So you got to write all that for all these. Some of these are special characters as far as regular expressions are concerned, like the square brace here, right? In regular expressions, that means that either the character 1, the character 2, or the character 3. So some of these punctuation marks have special interpretation. You need to ensure that the special interpretation is not taken in the regular expression, which means you have to either quote it or some people call escape it. So you could put backslashes in front of all these. I think the easier thing to do is what you can do in Flex is you can simply surround it by double quotes, and that means give it its literal meaning, not its special meaning. In fact, what I would do is I would actually not even think about it. I'd just go into every single one of these, and I'd just surround every single one of these with double quotes. And don't worry about whether you need to do it for this one or that one. Just do it on all of them. So do it on all these, all those, all those. And then we get to the bottom here, and these are the ones where you're going to have to write more complex regular expressions. So remember that exercise we had that pain in the butt expression that matches a double? Okay, that's done here. Note that you can have more than one, right? You can have something here, and you can and then you could have some totally, oh, darn it, sorry, caps lock. Then you could have some totally different regular expression. It could still return the same thing. There's nothing wrong with any of that. So you have to do those. All right. Yes?
So the T-double token is for when you actually find the word double in the GPL file, and then the constants for like the actual literal double value, like 1.3 would be.
Right. So if I have double XYZ semicolon, that's T double. Is it double constant? I'm guessing. We can double check in a minute. And then this would be like T semi or something like that. So those are the tokens that would go from the scanner to the parser. If I quickly look at tokens for bison, and I search for double. So it's T double constant and T double, and then if I look for semi, T semi C for semicolon. Yeah.
Do variable identifiers have their own token?
Do variable identifiers have their own token? So you would have a regular expression here, and then it would return TID. So that would be an identifier. Now, it feels a little bit untethered to imagine going away and trying to make all these things suddenly come together. Well, that's where this helps, right? It's going to step you through it a little bit. That isn't to say there aren't big chunks of things that you need to do on any one item, but at least it's going to put it in an order so that you're able to constantly move forward. So let's see if I want to go into detail on any of these. A lot of this explains stuff that I've talked about to one extent or another. The angle braces. At this point it says go ahead and run bison on your parser file. There will be over 200 shift reduce conflicts. But you just when you get to this point, seeing the conflicts is fine, but there should be no errors. So at this point you confirm there are no errors, and then further down you eliminate the shift reduce conflicts. So now you deal with the scanner. So you deal with the parser first, then you deal with the scanner. Here it's showing you how some of that looks. Here it's showing you how to deal with that the line count variable, creating the regular expressions. And then here's where you start dealing with associativity. It refers you to probably to look at a precedence chart to make sure you get them all right, because there are a lot of operators. The couple non-associative ones, a couple things we haven't talked about, which we can talk about once you're getting your toes wet with this stuff. And that's that. So how do you test this thing? you'll note there's a directory called tests inside of P1. And if I look up to where the tarball was extracted, remember there are two directories. There is a source directory, which is what we're in, which has all the project directories. And then there's a bin directory. And the bin directory has tools to help you test and debug. And for that, I'm going to go here. All right, so this is one that I've already completed the project here. And what I want to do is I want to run a series of tests and see if my code is working correct. I can type make and build my project. You may get this error, which has modification time sometime in the future. This is a symptom if you're using Vagrant, and it's a mismatch in the current time between your host operating system and the virtual machine. And since you're using a mounted directory, mounted on the host being used from the guest operating system, the times aren't going to match, and make will complain at you now and again. And you get the clock skew detected. That's what it's talking about. You can basically just ignore that. All right. So that actually created my GPL program. But I need to test it and see if my GPL program is meeting all the requirements of Project 1. There's a directory here called tests. Let me look at that. And let me actually look at a subset of these so that it isn't quite as harsh on the eyes. Tests. Let me do it again. All right, there we go. So the format here of these tests is the letter T and then some 3-digit number. In later projects, you get into, I think Project 5 has over 200 tests. There aren't very many this early on. There are 3 files. Note the middle one shown there is the .gpl file. This is a chunk of GPL code. Some of that code is perfectly fine. Some of that code is intentionally buggy. And it is to test, at this stage of the game, it's to test to see that your scanner is scanning things appropriately and getting information to the parser appropriately. So I can look at, just for the sake of looking at it, let me look at test4.gpl. Oftentimes there are comments in these that are helpful in understanding why the test exists, and I'll give you a really good example of why these comments are useful in a minute. They aren't in all the tests, but they are in several of them. And this is, I think this is testing a bunch of valid code. It's nonsensical code, but it can be a nonsensical code because the parser's empty. You aren't doing any meaningful work in the parser. So that's what test 4 looks like. How do you run the, and then there's .err and .out. That is, for this test, what is the expected error output? Let's look at the expected error output for this. Okay, 0 lines, 0 characters. There's no expected output. Excuse me, there's no expected error output. As far as the output that's expected, it's expecting to see this output. No, let me actually, you wouldn't normally do this, but we can try it manually. Let me clear the screen. I'll run my GPL program that I just compiled, and I want to run, there we go. How do I run all the tests? If I go, let me see, where am I? cd ... bin, let me ls, let me clear, and ls, get it all in one column. memvalidate.bash is a tool I have to make sure you don't have any memory leaks. That isn't going to be useful to us until a later project. What we are concerned with immediately is this GT. And this GT, I don't know what the GT stands for. Go test. Means to test things. So I can go up to my bin directory, and you can put this in your path, right? So you don't have to type this, so you can just type GT. And it'll run the tests, all the tests. And it passed all the tests except one, and you can see that it failed there. Gesundheit. And on the failed test, sometimes only the standard out will be incorrect, sometimes only the standard error would be incorrect. If it's one or the other, you'll see that. In this case, both of them are incorrect, so it's showing you that. So what you can do then, let me do that ls again, is VD and VDE is to be able to, VD stands for vimdiff, is to look at the differences between the output that your program produced and the output it's expecting. So let's look at VD. And then what VD wants is a test number to examine. And it was test 17 that was messed up. You can say 017. You can omit the leading zeros if you want. So I can just do this. And if you look at the bottom, you'll note that the left-hand pane is tests, t017.out. That is what it's expecting. And on the right is a results directory, test017.out. That is what your executable produced. So you want what's on the left and you got what's on the right. And it looks like test 17 is supposed to generate some sort of error because it's expecting to say that, hey, you got 2 errors. But my version of the program thought everything was great. At this point, you can get out of this. If you're unfamiliar with Vim, and you're not a Vim user, first of all, my condolences. You're going to die penniless and alone. But otherwise, the way you get out of this is you just type :QA if you're unfamiliar with Vim. So just type, which means quit all. So that'll quit everything, bring you back here. And now, just for the sake of doing it, we can look at the VDE, which is to look at the error differences in error output. And this is showing what the actual error is. It's expecting the error, syntax error on line 4, caret is not a legal token, and mine didn't have any error output at all. So, you ask yourself, well, how in the hell am I going to figure out what the problem is? A great place to start, other than looking at those error messages, is to look at the actual test. So I'll bring up in my editor, I'll go to the tests directory, and I'll look at t017.gpl. That's the code that it ran. And there is a hard to read, there, that's easier to read, comment. If you use the regular expression, a through lowercase z, you'll think this is a legal identifier instead of an error. To get just the letters to do this. I actually talked about this in a previous class. We looked at the ASCII chart, and we saw there were a series of characters between uppercase z and lowercase a, and that's what this error is. And I intentionally put this in my flex file when I was searching for identifiers. And you can see that it is a bogus test, right? You should get a syntax error here. And mine didn't because it thought that that was one of the legal characters comprising an identifier. Yes?
It's like the numerical value of the XOR is between the uppercase characters and lowercase characters.
That's exactly right. It's between uppercase z and lowercase a. As far as the ASCII values go, yeah, falls in between. And so there are a lot of tests like that, right, to make sure you're using doubles correctly. If we were to crack open the tests, I think there's some tests that have like 32.32 point, something like that, to give you errors in double constants. So it'll make sure that all your regular expressions are correct. I think that about covers what needs to be done. You'll note here that there's a results directory. So that is, it ran all the tests, and these are the results that your, in my case, my GPL executable created. Not interesting to look at, but you can. You can see that all my output and error output is included, and it puts in a little empty file saying passed. That's just note keeping for the GT tool. The GT tool is intelligent. It uses this little passed flag because if I go up there again and run GT again, it doesn't run all the tests. It just runs the tests that I'd failed. And that isn't that big a deal. You saw that it ran these tests very quickly. When you get to the third project where there are over 200 tests, the tests are more complex, it saves you a lot of time if you're just focusing on the broken tests. After you get everything working, you want to make sure you didn't break anything that was working to begin with. So there's even a comment here on the GT tool. You can say -all to force it to rerun all tests. Okay. Or you can pick out a specific test if you want it to run. All right. So, are there any questions? Yes?
Yeah, can you test multiple at a time, like 16, 17, or whatever?
I don't believe so. I believe it's, yeah, it's not going to do it.
It's kind of interesting in how it happens.
It's, you can look at it, right? It's these aren't complex executables. You can crack them open. It's just a shell script. Yeah. So.
It just seems like it's going to bother printing out past like 1 out of 1 instead of just.
Yeah, yeah, it's primitive. Take 344 and make it a project you do to enhance this. Any other questions? All right. So what I want you to do then is I want you to crank on this for 48 hours. And on Thursday, I'm going to take your questions that you have on this. This one is not a large project. It's not too terribly difficult. There is a lot to it, and you can get lots of typos, but it isn't mentally too taxing, definitely compared to the later projects. Project 2, you start to have to write a lot of C++ code. Not here, right? We're just trying to get all the stuff inside of the scanner and parser files. So you need to work on it over the 48 hours, either get it done or come up with problems that I can help you with. It's going to be due prior to Tuesday's class because we're going to move forward with the next project on Tuesday. All right. So with that, I will cut you loose a little bit early.